Welcome to Calculus 1, Chapter 2, Section 8, where we are going to talk about the derivative as a function. We'll go through and look at some slides and talk about the derivative a little bit more generally and conceptually. We'll look at a couple of processes for relating a function to the graph of the derivative of the original function. So we'll see the graph of the function and the graph of its derivative. And I do want to go through one homework problem where we will work through yet another derivative, and we'll be using the limit method in order to find that derivative. Let's check it out. So our first derivative, evaluated at an x value of a, can be determined by taking the limit as h goes to 0 and applying it to the difference quotient, where the difference quotient is interacting with our function, in this case f. If we didn't want to evaluate the derivative for a specific value of a, we could come up with a general derivative, leaving it in terms of x, and we could then plug a variety of different input values or a values into that first derivative once we have it figured out. So what we're seeing here is that f prime of x, which is actually a specific value once we plug in an x value, but that f prime, that first derivative, is indeed its own function, and we call that new function the derivative of our original function, in this case f. If your original function was function g, then the first derivative of g would be g with that little mark next to it. We also sometimes read that as g prime. Remember that our first derivative is sort of graphically or geometrically being interpreted as the slope of the tangent line to our graph at a particular point on our graph, and that can also be articulated as the rate of change, specifically the instantaneous rate of change of the function at that point. And here in this first example, we're being given the graph of a function, and we want to use it to graph the derivative, which, as I mentioned, is a new function which does have its own graph. And in order to do that, it's recommended that the first thing we look at are, so this blue curve is showing us our original function, and it's being recommended that we first look at these points on our graph where the slope of the tangent line is equal to 0. And if we take those 3 points, or x values, essentially what we're going to do, or specifically what we're going to do, is we're going to graph this x coordinate with a new y value. And that y value is going to be the slope of the tangent line. At this x value, the slope of the tangent line is 0. At this x value, the slope of the tangent line up there it is 0. At this x value, the slope of the tangent line is 0. So we're going to be graphing maybe 0.4, comma 0, 1.4, comma 0, and 3, comma 0. And then another thing that we could do is we could sort of work our way from left to right, and maybe give me a different color with a bigger pen. Yep, that's good. We could then go in, I don't want to do blue though, let's do purple. We could then go in and start looking at maybe when, let's see, yep, there we are, right there, where x is equal to 0, we could examine the slope of the tangent line and say, well, it looks like maybe it's -1. And when x is equal to 1, we could check out the slope of the tangent line and say, well, that's equal to +1. And when x is equal to 2, the slope is equal to, we're sort of estimating here. Maybe it's equal to -2. And we could keep going through, specifically looking for some points that are in between these 0 slope points and finding some other points that we could estimate the slope of the tangent line at those points and use those in order to plot some additional points. The one that's pre-printed for us here is this one. When x is equal to +5, this illustration is telling us that the slope of the tangent line is approximately 3/2. So what we're going to do is the original marks that I put in red, we're going to take those x coordinates and bring them down and see that the point that's plotted, as I said, is approximately 0.4, 0, and 1.4, 0, and 3, 0. And then that last point, which was a little different, up here, we said, well, when x is equal to 5, the slope is equal to approximately 3/2. So let's come down here to 5 and plot a point 5, 3/2, or 1.5. The rest of the graph that we're seeing in sort of pink here is the graph of f prime, the first derivative, a new function. How was the rest of this graph determined, the rest of this curve? Potentially by doing what I was saying up here in purple, is finding some other points on the original function, estimating the slope of the tangent line of those points, and then plotting some additional points, and then sort of sketching a curve through those points. Let's look at one example. What about this point right here, 0 for an x value? I said that the slope is approximately -1, the slope of the tangent line. Let's go down here to the graph of our original, or our derivative, f prime, and for an x value of 0, we have a slope of approximately -1. So we could have plotted that point there also, in addition to this point, and this point, and this point, and this point way up here. And then, again, we're roughing in or estimating our curve drawn through those points. The more points you have, the more accurate the graph of your first derivative is going to be. It's an unusual process, and here the author has provided us some articulation about what's happening there, and you're more than welcome to read that in his words. I'll leave that up just for a moment. Repeating the process at several points, we get the graph shown below. And there's the graph shown below, the one that we were just looking at. A horizontal tangent line has a slope of 0, therefore the derivative is equal to 0 at a point with a horizontal tangent line. So here's another opportunity for us to try that process. We're not being given any marks on the x or y axis, so that makes it a little bit challenging, but surely at whatever x value this is, the slope of that tangent line is quite steep, at least it looks pretty steep, and it's a positive slope. Maybe that has a slope of +3 or 4. And then this point, when x equals 0, has a slope of 0, and when x equals maybe 1, we're at this point with a slope of, well, it's a negative slope, but it's not very steep. Maybe it's a slope of -1. And when x equals 2, we've got a slope that's negative, but still not very negative. Maybe that has a slope of -1/2. So we could start trying to plot those as points. So at -1, I said we've got a pretty steep tangent line. So maybe that has a slope of +3. And up here where x equals 0, the slope of the tangent line was horizontal, so a slope of 0. So I'm going to plot the point 0, 0. And when x equaled +1, I set a slope maybe of -1. So let's come down 1 unit and plot 1, -1. Up here where we had the x value of +2, I said, well, the slope is still negative, but it's maybe not quite as negative, so maybe it's only a slope of -1/2. So maybe the slope, or maybe the graph of f prime looks something like this. Well, except for the last part of that. It looks like the slope of our graph as it goes off to the right is going to remain negative, but less and less negative. So I'm going to bring this up and keep it negative, but I'm going to get it pretty close to the x-axis there. And sure enough, that was a pretty good estimation. We chose enough points on the original curve function f in order to plot some points and approximate the graph of f prime. Remember that all of the x coordinates stayed the same. This x is this graph. Here we go. This x coordinate stayed the same. This x coordinate stayed the same. Stayed the same. Stayed the same. What changed, though, as we went from our original function down to the graph of our first derivative function? The y values got changed. We replaced them with the slope of the tangent line. In other words, f prime of -1, f prime of 0, f prime of an x value of 1, f prime of an x value of 2. Those became our new y values. In your homework assignment, my students are going to have the opportunity to work a bunch of problems where you need to go through that process, and there are some examples that you'll have access to. So never fear, you're going to be experts at this process very soon. In this example, we see on the left the graph of the square root function, and on the right is the graph of the first derivative of the square root function, which is this function here. So that's this graph. Oop, it's written below it. I don't have to leave that there. There it is. So here's the square root of x, and here is the first derivative of that function. And as our original function, the square root of x, gets in here really close to an x value of 0, it's hard to tell exactly what's happening there. And so it might be, well, it would definitely be beneficial to actually calculate the first derivative. So in this case, we have the opportunity to do that. We could take our original function f of x equals the square root of x. We could calculate the first derivative. And look what happens if we take an x value that's quite small. In other words, an x value that puts us just to the right of the y-axis. If we plug in an x value like, I don't know, 0.01 maybe, and we take the square root of 0.01, we take the square root of that, we get 0.1, we multiply it by 2, now it's 0.2, and then that's our denominator, so we've got 1 divided by 0.2, which is equal to 5. So if you look at this graph that's up here, with an input value of 0.01, we have to go up to a y value of 5. So as our x values are getting closer and closer to the y-axis from the right, our y values are becoming extremely large, In other words, the limit as our x values approach 0 from the right, that's a little plus sign there, on this derivative function, the y values tend toward positive infinity. There it is. It won't stay there. I have to hold it, otherwise it snaps back. So again, some of the functions are going to be a little bit more difficult to sketch what you anticipate the first derivative function to look like, and it will end up being beneficial to actually go through the motions and calculate the first derivative. Some other notations that you might run into. This is not going to be a long conversation, but this is something that you might want to have in your notes. We've got f prime of x. F of x and y equals have for some time now, certainly since maybe a college algebra class, we've thought of those as being kind of interchangeable. So f prime of x and y prime. Shouldn't be a big surprise that those two are interchangeable. And then we see dy over dx. This is really a lowercase delta y over lowercase delta x. And remember that delta represents change. Back here where we said that f and y were kind of interchangeable, now we're seeing that as y and f being interchangeable. It is also acceptable notation to say that we're taking the first derivative with respect to x of the function f of x, or this capital D, or capital D meaning the derivative with respect to x of whatever your function is. I would say that these two notations are less frequent, and for that matter, from left to right, we're probably decreasing in the likelihood that you're going to see this notation. So f prime of x will be the most frequent kind of notation that you see. In fact, I'd say these three are really big, maybe even these four are really big. In terms of the frequency with which you'll see those notations. And then these ones that are over here on the right, you're less likely to see those. But just be aware that they exist and are used. Lowercase delta, uppercase delta. We're talking about Greek letters now, all right? So the first derivative of your function or your equation y, that first derivative is equivalent to the limit as the difference in those x values tends towards 0. Remember that this delta x down here we are often seeing represented as the lowercase h. So usually I would say even that it's as h tends towards 0. These are notations that I in my mathematical career have seen much less frequently. That if you take a derivative and you want to evaluate it at a particular value, we're seeing this bar with the x equals a, or sort of half of a square bracket with the x equals a. I don't see this very often when I'm working with derivatives. When we're working with integrals or antiderivatives, definite integrals, you will see this notation, and there will be an additional value up at the top of it. But I don't know, I would say that this is what you're going to see 99% of the time. And then we have a definition, so of course this is important because it's in its own little dedicated blue box. A function f is differentiable at a if f prime of a exists. Well, that's nice. if it is differentiable on an open interval, so if you are told that a function is differentiable on an open interval, and when I say open interval, I'm talking about this. And it's an open interval because it has parentheses at either end. If it were a closed interval, it would have square brackets. So if it's differentiable on an open interval, that means that your function is differentiable at every number in that interval. So you could take your first derivative and you could plug in any number you want as long as it's between a and b. Example number 5 takes a closer look at the absolute value function. I don't want to get too tangled up in this. The absolute value function is actually a piecewise function. The absolute value of x, defined as a piecewise function, says that if your x value is greater than or equal to 0, then the absolute value function just returns your original input value. What's the absolute value of 5? Well, 5, right? What's the absolute value of 0? 0. But if the x value that you plug in is less than 0, for example, what's the absolute value of -3? The answer is +3. Well, how did you change a -3 into a +3? I negated it again. I took the opposite of it. So if your x value is less than 0, then your absolute value function is going to return the opposite of your input value. You need to keep this in mind in order to go through and read this solution process, which I'm not going to spend a lot of time on, but notice that here's this distinction that if x is greater than 0, then we find our first derivative using the limit process. Here's x plus h, so that's that's f of x plus h minus f of x, and since our x value was greater than 0, we have abandoned the absolute value bars. X value is greater than 0. We let go of those absolute value bars, and then we finish evaluating the limit, and we find that if our x value is greater than 0, which is hiding behind me there we go. If our x value is greater than 0, then the first derivative is equal to 1. For which x values is my slope of my tangent line going to equal 1? For all of the x values greater than 0. Similarly, for x values that are less than 0, as I talked about as part of the piecewise function, the absolute value of a negative value, we return the opposite of that negative value. And since x is negative, here it is, x is negative. If we add an h value to it, where that h value is crazy small, even if it's a positive h value, I can make the h value small enough that x plus h is still less than 0. Therefore, the absolute value, now check this out, the absolute value of a negative number, when you take the absolute value of a negative number, you return the opposite of that original input value. So in this case, where x was less than 0, or where x is less than 0, and x plus h is still less than 0, the absolute value of x plus h can be interpreted as the opposite of, or negative, x plus h. Therefore, as we go through the process of finding our first derivative, we take the limit as h goes to 0 of f of x plus h minus f of x. But remember now, x is less than 0, and we're interpreting that as the opposite, so we're returning the opposite value. Here we're returning the opposite value from our absolute value function. Process, first derivative is equal to -1 for x values less than 0. So f appears to be differentiable for x values that are greater than 0 or less than 0. And what about when we have an x value that is 0? If we go through all of the motions, we find that we get this statement. Now, we haven't concluded the process of evaluating the first derivative at 0. First derivative at 0. We sort of stalled out here. And remember that the limit as h approaches 0 can only be determined if the limit from the left equals the limit as we approach from the right. However, we just saw in the previous couple of slides that for all of our x values that were greater than 0, the limit was equal to positive 1, and the limit for all of the x values that were less than 0 or left of 0 was equal to negative 1. And negative 1, as you well know, does not equal positive 1. Therefore, it appears that the first derivative of the absolute value function cannot be determined when x equals 0, because the limit from the left does not equal the limit from the right. We're seeing the graph of f prime right here. They don't match up, so that limit does not exist. And if that limit doesn't exist, then the first derivative does not exist for, or at, or when x equals 0. Here's the graph of the original absolute value function. You can see that the slope of this line is positive 1, the slope of this line is negative 1, but what's the slope of the tangent line here? I don't know. It can't be determined. That's what we just determined, is that it can't be determined, because the limit from the left does not equal the limit from the right as pertains to the first derivative. We like things to be continuous, we like them to be differentiable. If a function is differentiable at a point, then the function is continuous at that point. But the converse, which is a logistical term, the converse is not necessarily true. In other words, just because a function is continuous does not necessarily mean that it's going to be differentiable. This function's continuous, however, it's not differentiable at this vertex. Continuous but not differentiable. If a function is differentiable at a particular point or for a particular value a, then the function is continuous there. I'm not going to walk you through this entire proof process. I'll scroll through it slowly. You're welcome to pause and check it out. If you want to download these notes and look at it in greater detail, be my guest. If a function is differentiable, then it's continuous. In order for the function to be differentiable, the first derivative as you approach from the left has to equal the first derivative as you approach from the right, and your function has to be defined at that particular point. How can a function fail to be differentiable? Well, there's this one, the absolute value function, which we just saw, which is an example of a function that has a kink or a corner. You could say that it's sharp at its vertex. And we saw that the first derivative as we approach from the left and as we approach from the right were not equal to each other. Even though the function is defined at the vertex, it has a y value, we could not figure out f prime at the vertex. If a function is not continuous at a particular point, I highlighted this already for us, then the function is not differentiable at that point. So if you have a hole there, or an asymptote, your function is not going to be differentiable. And thirdly, if you have a vertical tangent line, can that happen? Can you have a vertical tangent line? then your function is also considered to not be differentiable at that point. So here we have a vertical tangent line. That's one way that a vertical tangent line might manifest. That's less common than seeing something like this. So even though there is a tangent line, even though the function is defined at that point, it's not differentiable. Why would that be? What's the slope of the tangent line here? I'd say it's negative. What's the slope of the tangent line maybe here? I'd say that's also negative. What about the slope of the tangent line right here? Ooh, I would say that that's very negative. Okay. And what about as we come in from the right? Negative sloping tangent line, and at this point, very negative sloping tangent line. It looks like they're approaching the same thing. And they are. They're both approaching a very extreme value. And once we actually arrive at this point that has an x-coordinate of a, the slope of the tangent line is maybe negative infinity. And so we're going to say that that constitutes a first derivative that is undefined. In order to have a tangent line with a slope that is positive or negative infinity, we would have to be dividing by 0. And we know that division by 0 usually returns an answer, so to speak, of undefined. So here are the three different scenarios. If you have a sharp corner, if you have a discontinuity, or if you have a vertical tangent line, we will say that the function is not differentiable. That should be in your notes. Okay, so let's look at a couple of examples, and these are going to be very similar to what you'll see in homework. This is pretty much where we started our conversation in this lesson. At this x-coordinate right here, the slope of my tangent line, or for that matter, the slope of my graph, the rate of change of my graph is, I don't know, maybe negative 1/2. So let's, it's tough without any markings on the x or y axis, but let's call this maybe -1. And so let's plot, we'll keep the x-coordinate the same, and we'll come down and say it has a slope of -1/2. What about at this point right here? Oh, that also has a slope of -1/2. And what about at this point right here? Also -1/2. So it looks like the slope or the rate of change of our graph for that sort of left-hand portion of our original graph has a rate of change that's about -1/2, right? Again, I have no idea because there are no markings on the y-axis. What about, let's now look at this segment right here. At every point on this segment, it looks like maybe we have a slope or a rate of change of +1. So I'm going to stick with purple, and I'm going to come up here and say, well, maybe this is +1. So I'm going to say on that entire interval, we've got a slope of +1. And then on this interval here, it looks like we have a slope of -1. So I've drawn my purple line down there. Every point has a y value, a slope value of -1. And then on this interval, we're back to a gentler slope, except it is positive. So for all of these x values that are in here, I'm going to keep those x values the same, but I'm going to plot points that have y values of 1/2. In other words, slope values or rate of change values of 1/2. Now what about at the actual sort of corners that we're seeing here? What's happening right there? Well, we know from our conversation that we just had that if you have sort of a sharp corner or a kink in your original function, in that original graph, that your derivative is not defined there. So I'm going to go in and put open circles at the end of each one of these little purple line segments that I just drew. and say that our first derivative is not defined there. I didn't do a very good job here. Let me back that up. Put in my open circle here, and an open circle down here, and an open circle, and open circle. Oops. There we go. And yes, Sophie, I hear you. All right. So that is the rough sketch of the first derivative of our function f. In other words, that's the sketch of f prime. And there we go. The author has given us a representation also of the first derivative of our function. What do you think? Have a look. You just missed me. You don't want to do any math. All right. What else do we have? Higher derivatives. So far you've heard me saying first derivative, first derivative. Are there other derivatives? Absolutely. If you took the derivative of the derivative, you would be looking at or working with the second derivative. There are some different notations here for you to examine regarding the second derivative. And then here's an example. If our original function f of x is x cubed minus x, we're to find and interpret the second derivative. This would be a good exercise for you to go through and tackle. Start with that original function f, use the limit process in order to find the first derivative, and then go through the limit process again in order to find the second derivative. What we've been given here is the original function, and then the author gave us the first derivative and asked us to use the first derivative in order to find the second derivative. So there's the beginning of that process. And after going through the motions, we find that the second derivative is 6x. And here's the graph of all three of those functions, the original function, the first and second derivative. So again, that'd be a good exercise for you to do in practicing finding your first derivatives using the limit process. Start with that function and you've got two answers there, first derivative and second derivative. All right, I don't want to look at this or this or this with you. So the second derivative can be interpreted as the rate of change of the rate of change, right? Because the first derivative was already the rate of change. So now you've got the rate of change of the rate of change. And the most familiar example, or the most frequently seen example of using the second derivative is in the relationship between velocity, or I should say position, velocity, and acceleration. If your if your position equation is lowercase s, then what we're seeing at the bottom of the screen here is that s prime of t, so the first derivative of your position function, is your velocity equation. And then if we go a step further and we take the second derivative of the position equation, which is equal to the first derivative of the velocity equation, we arrive at an equation or a function that describes acceleration. So I got there by, if we took the first derivative of both of these functions, so this already is a first derivative. So if I take the derivative again, I will have the second derivative of the position function, s double prime, which is what you're seeing right here, s double prime. And then we took the derivative of the velocity function. Now that's not a derivative yet, that just says v of t. We come down here, we have taken the derivative of it, that's why it says v prime of t. And what we've just learned is that the first derivative of the velocity equation is an equation that describes acceleration. Using different notation, you can see that written there. Is it possible to take a third derivative? Absolutely. Could I keep taking derivatives until I fall over? Definitely. I've done it. something that you'll maybe never see, maybe never, maybe once. I don't know. I don't think I ever see this, but it is true. The third derivative of the position equation, which is the first derivative of the acceleration equation. Let me say that again. The third derivative of the position equation, which is the first derivative of the acceleration equation, is referred to as the jerk. And there's some notation for you there. And the jerk is indeed the rate of change of acceleration. And you can imagine if you were accelerating fairly slowly and then you in your car and then you stomp on the gas pedal, your rate of acceleration is going to change. Now you're going to be accelerating much faster. And that kind of an abrupt movement is what compelled someone to refer to the derivative of the acceleration equation as the jerk. Any of those higher derivatives, I don't know if I've seen this for a third derivative, but definitely a fourth derivative, you end up with too many of these little tick marks next to the name of your function. And so we just put the, how would you say it? Generally speaking, this notation represents the nth derivative, and so you would put, for a fourth derivative, you would put a 4 in these little parentheses up here to indicate how many times you're taking the derivative of the original function. All right, so there's some conceptual stuff and a couple of process-oriented things regarding not just the first derivative, but we went all the way to the third derivative that's applied to the position of function, and then you saw notation for higher derivatives, the nth derivative there. And now let's pop over to the homework. This is exactly what we did at the beginning of this lesson, where you're examining each of these graphs in red and trying to match them up with the corresponding graphs of their first derivatives. So I've already talked about a process you can go through to do that. The same here, and you can click in. My students get to click in and check out an example of that process, so you're welcome to do that. Here, same thing. What's the slope of the tangent line here? What's the slope of the that's the cat walking on the iPad. There we go. What's the slope of the tangent line here? What's the slope of the tangent line here? Oh, baby, not on the keyboard. That's not a good idea. Still recording. Good. She didn't hit any unusual keys there. And I think we actually already did this problem as part of the notes. So that one should be pretty straightforward. Here, this looks like at some point on this blue curve, you're going to have a tangent line that is vertical, which means the first derivative will be undefined at that point. And then number 6, this is the one that I thought maybe we should do together, just to go through the motions of manually taking a first derivative again. So here we're being given this function. Zoom it in a little bit. 3t minus 4t squared. Our first derivative, not at a particular value, we're just leaving that independent variable t in there, is equal to the limit as h approaches 0 of f of t plus h minus f of t. Remember, that's y2 minus y1 that we just did there, all divided by, now x2 minus x1 is h, so that's why we put an h in the denominator, and we're going to get those x values really close to each other, which is why we're setting our h value to 0. So let's plug in the t plus h. Let's see, let's keep writing out our limit as h goes to 0. Now plug in the t plus h. That's 3 times t plus h minus 4 times t plus h squared. which is t squared plus 2th plus h squared. And then we have to subtract f of t. So I'll switch colors here and say minus f of t, which is 3t minus 4t squared. That's, in fact, let me move to the left. So right here, this f of t right here, I'm going to erase that and write it in purple so that it matches with this other stuff that I just wrote in purple. Let's go in here, just in case you also like using two different colors. I don't do this all the time, but depending on the process, sometimes it's nice to have a couple of colors. Can I make that darker? No. Okay. And then we're dividing all of that by h. All right, so this is equal to the limit as h goes to 0 of 3t plus 3h minus 4t squared minus 8th minus 4h squared minus 3t plus 4t squared. So I distributed this minus sign up here. This minus sign I had to distribute to both terms. All right, that's how I got these two terms. And as you might recall, those two terms better cancel out with something earlier in our expression. If they don't, we know that we've done something wrong. Close our brackets, divide it all by h still, equals, let's keep going, the limit as h approaches 0 of positive 3t is canceling with the negative 3t, minus 4t squared is canceling with the positive 4t squared. So all we have left is a positive 3h minus 8th minus 4h squared, all divided by h. Now I'm going to distribute my division. The h in the denominator is going to cancel out a factor of h from each of the terms above it. So this h is going to cancel out this h and one of these h's. So I'm just canceling out that exponent there, which means that we can now write this as the limit as h goes to 0 of 3 minus 8t minus 4h. Now we can finally apply the limit. It's a polynomial, so we can use direct substitution and say that our first derivative, f prime of t, is equal to 3 minus 8t. Because this term became 0 when we plugged in an h value of 0. That says minus 4h there. All right, so just a reminder of the process to go through using limits in order to find the first derivative of a given function. Be careful, be organized, spread out, use lots of paper, skip a line here and there in order to keep each one of these stages of the process well defined. Here's a question about where our function is not differentiable. Another about where our function's not differentiable. Another about where our function's not differentiable. So this assignment is considerably more conceptual than usual, but I really wanted to go through and look at that more algebraic looking process of evaluating the limit using the difference quotient, because that can be Very challenging. These other questions that are more graphically oriented are more visual, and my assumption is that fewer people are going to struggle with those once you get the concept nailed down, but connecting that concept to the more algebraic part of the process of using the limit to find the first derivative is tough, so make sure that you keep your skills up on that. Eventually we won't have to do that as often, but still very important to know what's going on behind the scenes in finding your first derivative. And I think this is the last time I'll see you in this section, so I will see you again in our next chapter. Thanks so much.